Let me tell you something that took me decades to truly understand. Quantum mechanics is not weird. I know that sounds strange coming from a physicist. Everyone says quantum mechanics is weird. It's practically a cliché at this point. But I've come to believe that quantum mechanics isn't weird at all. What's weird is our expectations. What's weird is that we ever thought the universe should behave like the world we see with our naked eyes. I'm going to take you on a journey through quantum mechanics, not the sanitized version you get in popular science documentaries, not the mystical nonsense you find in New Age bookstores. The real thing, the mathematics made intuitive, the philosophy made precise. And I promise you, by the end, you won't think quantum mechanics is weird anymore. You'll think it's inevitable, but first I need to destroy something. I need to destroy the picture of reality you've been carrying around in your head since childhood. The picture where things exist in definite places, where causes precede effects in neat little chains, where the universe is basically a giant clockwork mechanism ticking away according to deterministic laws. That picture is wrong, not approximately wrong, not wrong in some technical sense that doesn't matter for everyday life. Fundamentally, deeply, irreparably wrong. Here's where it starts. In the early 1900s, physicists began noticing things that didn't fit the classical picture. Light, which everyone knew was a wave, sometimes behaved like a stream of particles. Electrons, which everyone knew were particles, sometimes behaved like waves. Matter, which was supposed to be solid and definite, turned out to be mostly empty space with probability clouds where particles might or might not be found. The old guard tried to explain these anomalies within the classical framework. They failed. Every attempt led to contradictions, to infinities, to predictions that didn't match experiments. Something fundamental had to change. And in the 1920s it did. A new framework emerged, quantum mechanics, and it was unlike anything that had come before. Let me explain what quantum mechanics actually says. Not the interpretation, not the philosophy, just the bare mathematical bones of the theory. At the heart of quantum mechanics is something called the wave function. The wave function is a mathematical object that contains all the information about a quantum system. For a single particle, the wave function is a complex valued function of position. It assigns a complex number to every point in space. The square of the absolute value of this complex number gives you the probability of finding the particle at that location if you measure its position. But here's what's crucial. The wave function is not a probability distribution over definite states. The particle doesn't have a definite position that we simply don't know. The wave function is the complete description of reality. There is nothing more. The particle doesn't have a position until you measure it. Before measurement, the question, where is the particle, has no answer. Not because we're ignorant, because the question is meaningless. This is hard to accept. I know. I struggled with it for years. We're so used to thinking that things have properties whether we look at them or not. The moon exists when nobody's watching, right? Well, yes. The moon is a macroscopic object, and macroscopic objects behave approximately classically due to a process called decoherence, which I'll explain later. But at the fundamental level, at the level of individual particles, properties don't exist until they're measured. Let me give you an example. The double-slit experiment. You've probably heard of it. It's the most famous experiment in quantum mechanics, and for good reason. It contains in concentrated form everything strange and beautiful about the quantum world. Here's the setup. You have a source that emits particles, electrons, photons, whatever. You have a barrier with two slits in it, and you have a detection screen on the other side. You fire particles at the barrier one at a time, and you record where each particle hits the screen. Now, if particles were classical objects like little bullets, you'd expect to see two bands on the screen, one behind each slit. The particles would go through one slit or the other and pile up accordingly. But that's not what happens. What you see is an interference pattern. Bands of light and dark. Exactly like what you'd get if waves were passing through the two slits and interfering with each other. But wait. We're sending particles one at a time. A single particle can't interfere with itself, can it? If it's a particle, it goes through one slit or the other. How can it create an interference pattern? Here's what quantum mechanics says. The particle doesn't go through one slit or the other. It goes through both. Its wave function passes through both slits simultaneously and interferes with itself on the other side. The interference pattern emerges because the particle is in a superposition of going through the left slit and going through the right slit. Both possibilities are real. Both contribute to the final outcome. Now here's where it gets really strange. What if you try to catch the particle in the act? What if you put a detector at one of the slits to see which way the particle actually goes? When you do this, when you measure which slit the particle passes through, the interference pattern disappears. You get the classical two-band pattern instead. The act of measurement destroys the superposition. Think about what this means. The particle's behavior depends on whether or not you're watching. If you don't look, it goes through both slits and creates an interference pattern. If you look, it goes through one slit and behaves like a classical particle. The measurement changes the outcome. This is not some artifact of clumsy experimental technique. It's not that the detector disturbs the particle in some classical way. The effect is fundamental. It's built into the structure of quantum mechanics itself. Measurement is not a passive observation of pre-existing properties. Measurement is an active intervention that creates the properties it measures. I want to pause here because this point is so important. In classical physics, measurement is idealized as passive. You look at a system. You record its properties. The system doesn't care that you looked. It had those properties all along. In quantum mechanics, this picture completely breaks down. The system doesn't have definite properties until measurement. Measurement forces the system to choose, and the choice is genuinely random. This is where Einstein balked. He couldn't accept that God plays dice with the universe. He spent the last decades of his life trying to show that quantum mechanics was incomplete, that there must be hidden variables, deeper properties that determine the outcomes of measurements in advance. He failed. And we now know, through the work of John Bell and subsequent experiments, that hidden variables of the kind Einstein imagined cannot exist. Let me explain Bell's theorem because it's one of the most profound results in all of physics. Bell considered a scenario involving two particles that are entangled. Entanglement is a uniquely quantum phenomenon where the quantum states of two or more particles become correlated in ways that have no classical analog. Here's a simple example. You create a pair of photons in an entangled state such that their polarizations are correlated. If you measure the polarization of one photon and find it vertical, the other photon will always be horizontal, no matter how far apart they are. The correlation is perfect. Now Einstein thought this could be explained by hidden variables. Maybe when the photons are created, they're given secret instructions. If someone measures your polarization at this angle, give this result. The correlations would then be explained by shared information, not by any spooky connection between the particles. Bell showed that this hidden variable explanation makes specific predictions. If the correlations are due to shared information, there's a limit to how strongly correlated the measurement outcomes can be. This limit is expressed as an inequality, Bell's inequality. Quantum mechanics predicts violations of Bell's inequality. The quantum correlations are stronger than any hidden variable theory can produce, and when you do the experiments, quantum mechanics wins. Bell's inequality is violated. The correlations are real, and they cannot be explained by shared information. This means one of two things. Either the particles are communicating faster than light, which would violate special relativity, or they never had definite properties in the first place. The measurement outcomes were not determined in advance. They came into existence at the moment of measurement, and they came into existence in a correlated way across arbitrarily large distances. Most physicists accept the second option. The particles don't have definite properties until measurement. The correlations are a fundamental feature of quantum mechanics, not a result of hidden communication or pre-shared information. But notice what this implies. If the particles don't have definite properties until measurement, then what exists between measurements? What is reality when no one is looking? This is the question that has divided physicists for a century. Different interpretations of quantum mechanics give different answers. Let me walk you through the main contenders. The Copenhagen interpretation, the oldest and still most common, essentially refuses to answer the question. It says that quantum mechanics is a tool for predicting measurement outcomes. Full stop. Questions about what exists between measurements are meaningless, or at least outside the scope of physics. The wave function is not a description of reality. It's a description of our knowledge about the system. I find this deeply unsatisfying. It feels like a cop-out. Physics is supposed to tell us what reality is like, not just give us recipes for making predictions. But I have to admit the Copenhagen interpretation is internally consistent. It just has a very limited conception of what physics can achieve. The many worlds interpretation takes the opposite extreme. It says the wave function is reality. Nothing but the wave function. And the wave function never collapses. When you make a measurement, the universe splits. In one branch, you see the particle go through the left slit. In another branch, you see it go through the right slit. Both outcomes happen. Both branches are real. You just find yourself in one branch and not the other. Many worlds is elegant in a certain way. It takes quantum mechanics at face value. No collapse, no special role for measurement. Just the wave function evolving smoothly according to the Schrödinger equation forever. But it has a cost. The cost is an exponentially proliferating infinity of parallel universes, most of which we can never access or verify. That's a steep ontological price to pay. Then there's pilot wave theory, associated with David Bohm. In this interpretation, particles do have definite positions at all times. They're guided by a wave, the pilot wave, which is related to the quantum wave function. The pilot wave tells the particle where to go, and this guidance produces all the quantum phenomena. There are no superpositions of particle positions, no collapse, just particles following deterministic trajectories guided by a wave. Pilot wave theory reproduces all the predictions of standard quantum mechanics. It gives definite answers to the question of what exists between measurements, but it requires a special unexplained connection between all particles in the universe. The pilot wave is a field on configuration space, not physical space, and it responds instantaneously to changes anywhere in the universe. Many physicists find this uncomfortable, and there are other interpretations, objective collapse theories, which modify the Schrödinger equation to include spontaneous collapse events, relational quantum mechanics, which says that quantum states are always relative to an observer, and there's no absolute observer-independent state of the system. Cubism, which treats quantum states as representing an agent's beliefs rather than objective features of reality. I've thought about all of these interpretations for decades. I've gone back and forth, and here's where I've landed. I don't think any of them is definitively correct. I think the interpretation question is still open. Maybe it will always be open. Maybe it's not a physics question at all, but a philosophy question, and physics can only take us so far. But here's what I do know. Regardless of interpretation, the formalism of quantum mechanics works. It makes predictions. Those predictions are confirmed by experiment to extraordinary precision. Whatever quantum mechanics is telling us about reality, it's telling us something true. The details of that truth might be up for grabs, but the broad strokes are not. Let me tell you about some of those broad strokes. Things we know for certain about the quantum world, regardless of interpretation. First, superposition is real. Quantum systems can exist in states that are combinations of classical alternatives. This is not a statement about our ignorance. It's a statement about reality. The interference effects prove it. Second, entanglement is real. Quantum correlations exist that are stronger than any classical correlation could be. Bell's theorem and its experimental confirmation prove it. Third, measurement has a special role. Whatever your interpretation, you have to account for the fact that measurements have definite outcomes, while quantum systems in isolation can be in superposition. Something happens when a system interacts with a macroscopic measuring device. What exactly happens is interpretation dependent, but that something happens is not. Fourth, quantum mechanics is complete in a certain sense. There are no hidden variables of the kind Einstein imagined. The randomness of quantum mechanics is not due to ignorance, it's fundamental. Fifth, quantum mechanics is universal. It applies to everything, not just tiny particles, but atoms, molecules, macroscopic objects, everything. The reason macroscopic objects behave classically is not that quantum mechanics doesn't apply to them. It's decoherence. The interaction with the environment effectively suppresses quantum interference effects and makes the world look classical. But underneath, at the deepest level, everything is quantum. Let me talk about decoherence because it's crucial for understanding why the world seems classical even though it's fundamentally quantum. When a quantum system interacts with its environment, the environment becomes entangled with the system. The superposition that existed in the isolated system spreads out into the environment. And once that happens, interference between the different branches becomes practically impossible to observe. Here's a simple example. Suppose you have a particle in a superposition of being in two locations, left and right. If the particle is isolated, the two branches can interfere with each other, producing quantum effects. But now suppose the particle interacts with a single photon. The photon bounces off the particle and carries information about the particle's position into the environment. Now the particle and the photon are entangled. The state of the combined system is particle left and photon going left, plus particle right and photon going right. The two branches are now distinguished by the state of the photon. And if you only look at the particle, ignoring the photon, the interference between the branches is destroyed. The particle appears to be in a classical mixture of left and right, not a quantum superposition. In the real world, quantum systems don't interact with just one photon. They interact with countless environmental particles, air molecules, thermal radiation, the entire physical world around them. The entanglement spreads out into this environment extremely rapidly, far too rapidly for us to track. And once the entanglement is spread over millions or billions of environmental particles, the interference effects become completely unmeasurable. This is decoherence. It doesn't solve the measurement problem in the deepest sense. The wave function still doesn't collapse. All the branches still exist in some sense, but it explains why we don't see superpositions of macroscopic objects. It explains why the moon exists even when nobody's watching. The moon is constantly interacting with its environment, and decoherence ensures that any quantum superpositions involving the moon are immediately spread out into unmeasurable correlations with the environment. Decoherence is why quantum computers are so hard to build. A quantum computer relies on maintaining delicate superpositions while performing computations. But every interaction with the environment threatens to decohere the quantum state, destroying the superposition and ruining the computation. Quantum computers need extreme isolation from their environment, which is technically very challenging. Now, I want to talk about something that fascinates me, the relationship between quantum mechanics and information. In the last few decades, physicists have come to see quantum mechanics through the lens of information theory. And this perspective has revealed deep connections that weren't visible before. Consider this. Classical information is measured in bits. A bit is either 0 or 1. Any classical state can be described by specifying the values of some collection of bits. Quantum information is measured in qubits. A qubit is a quantum system with two states, which we might also call 0 and 1. But unlike a classical bit, a qubit can be in a superposition of 0 and 1. It can be both at once in a certain sense. This makes quantum information fundamentally different from classical information. A qubit carries more information than a bit in some ways. You can encode information in the continuous amplitudes of the superposition. But in other ways, a qubit carries less information than you might think. When you measure a qubit, you only get one bit of information, either 0 or 1. The rest of the information in the superposition is lost, or more precisely, it leaks out into correlations with the measuring device and the environment. Entanglement is the key resource that makes quantum information qualitatively different from classical information. Entangled qubits can be used for quantum teleportation, transferring the exact quantum state of a particle from one location to another without physically moving the particle. They can be used for super-dense coding, sending two classical bits of information using only one qubit. They can be used for quantum cryptography, generating perfectly secure encryption keys. And most dramatically, entangled qubits are what give quantum computers their power. A quantum computer with n qubits can be in a superposition of 2 to the n different classical states simultaneously. For large n, this is an astronomically huge number. In a certain sense, the quantum computer is performing 2 to the n computations in parallel. Now, you can't just read out all 2 to the n results. When you measure the quantum computer, you only get one answer. But clever quantum algorithms can arrange things so that the answer you get is the one you want. The interference between all the parallel branches cancels out the wrong answers and reinforces the right one. This is how quantum algorithms like Shor's algorithm for factoring large numbers work. Factoring is hard for classical computers. The best classical algorithms take time that grows exponentially with the size of the number. But Shor's algorithm, running on a quantum computer, can factor large numbers in polynomial time. This would break most of the encryption that secures the internet, which is why there's so much interest in building quantum computers and also in developing quantum-resistant encryption. But I don't want to give you the impression that quantum computers are just faster classical computers. They're not. They're a fundamentally different kind of computer that's good at fundamentally different kinds of problems. For many problems, quantum computers offer no speedup at all. For others, the speedup is modest. Only for certain special problems is there an exponential quantum advantage. What's remarkable is that these special problems exist at all. The universe has a computational structure that allows certain computations to be performed exponentially faster using quantum resources. That's telling us something deep about the nature of reality. I'm not sure we fully understand yet what it's telling us, but it's something important. Let me shift gears and talk about one of the deepest questions in quantum mechanics, the relationship between quantum mechanics and gravity. We have two great theories of physics, quantum mechanics and general relativity. Quantum mechanics governs the very small. General relativity governs the very large, especially where gravity is strong. Both theories are spectacularly successful in their domains, but they don't fit together. Quantum mechanics is built on the assumption of a fixed background spacetime, the stage on which quantum fields dance. General relativity says there is no fixed background. Spacetime itself is dynamical. It curves and warps in response to matter and energy. The stage is part of the show. Now I want to talk about something that fascinates me. The relationship between quantum mechanics and information. In the last few decades, physicists have come to see quantum mechanics through the lens of information theory, and this perspective has revealed deep connections that were invisible before. Consider this. Classical information is measured in bits. A bit is either 0 or 1. Any classical state can be described by specifying the values of some collection of bits. Quantum information is measured in qubits. A qubit is a quantum system with two states, which we might also call 0 and 1. But unlike a classical bit, a qubit can be in a superposition of 0 and 1. It can be both at once, in a certain sense. This makes quantum information fundamentally different from classical information. A qubit carries more information than a bit in some ways. You can encode information in the continuous amplitudes of the superposition. But in other ways, a qubit carries less information than you might think. When you measure a qubit, you only get one bit of information, either 0 or 1. The rest of the information in the superposition is lost, or more precisely, it leaks out into correlations with the measuring device and the environment. Entanglement is the key resource that makes quantum information qualitatively different from classical information. Entangled qubits can be used for quantum teleportation, transferring the exact quantum state of a particle from one location to another without physically moving the particle. They can be used for super-dense coding, sending two classical bits of information using only one qubit. They can be used for quantum cryptography, generating perfectly secure encryption keys, and most dramatically, entangled qubits are what give quantum computers their power. A quantum computer with n qubits can be in a superposition of 2 to the n different classical states simultaneously. For large n, this is an astronomically huge number. In a certain sense, the quantum computer is performing 2 to the n computations in parallel. Now, you can't just read out all 2 to the n results. When you measure the quantum computer, you only get one answer. But clever quantum algorithms can arrange things so that the answer you get is the one you want. The interference between all the parallel branches cancels out the wrong answers and reinforces the right one. This is how quantum algorithms like Shor's algorithm for factoring large numbers work. Factoring is hard for classical computers. The best classical algorithms take time that grows exponentially with the size of the number. But Shor's algorithm, running on a quantum computer, can factor large numbers in polynomial time. This would break most of the encryption that secures the internet, which is why there's so much interest in building quantum computers and also in developing quantum-resistant encryption. But I don't want to give you the impression that quantum computers are just faster classical computers. They're not. They're a fundamentally different kind of computer that's good at fundamentally different kinds of problems. For many problems, quantum computers offer no speedup at all. For others, the speedup is modest. Only for certain special problems is there an exponential quantum advantage. What's remarkable is that these special problems exist at all. The universe has a computational structure that allows certain computations to be performed exponentially faster using quantum resources. That's telling us something deep about the nature of reality. I'm not sure we fully understand yet what it's telling us, but it's something important. Let me shift gears and talk about one of the deepest questions in quantum mechanics, the relationship between quantum mechanics and gravity. We have two great theories of physics, quantum mechanics and general relativity. Quantum mechanics governs the very small. General relativity governs the very large, especially where gravity is strong. Both theories are spectacularly successful in their domains, but they don't fit together. Quantum mechanics is built on the assumption of a fixed background spacetime, the stage on which quantum fields dance. General relativity says there is no fixed background. Spacetime itself is dynamical. It curves and warps in response to matter and energy. The stage is part of the show. Let me bring this back to something personal. I've been thinking about quantum mechanics for over 50 years. I've calculated countless wave functions, wrestled with countless interpretational puzzles, debated with colleagues who see things differently. And through all of it, my sense of wonder has only grown. Quantum mechanics tells us that the universe is not what it seems. The solid world of everyday experience is built on a foundation of probability and superposition and entanglement. Things don't have properties until they're measured. Particles don't have positions until they're observed. The past is not fully definite until the present makes it so. Some people find this disturbing. They want the universe to be solid, reliable, independent of observation. They want a reality that exists fully and completely whether anyone is looking or not. Quantum mechanics denies them this comfort. But I find quantum mechanics liberating. It tells us that reality is richer than we imagined. It tells us that the universe is not a machine, but something more like a vast quantum computation, processing information, creating correlations, building complexity from simple rules. It tells us that we, as observers, are not passive witnesses to a pre-existing show. We're participants. Our measurements matter. Our choices about what to observe shape the very reality we observe. Does this mean consciousness plays a special role in physics? I don't think so. Consciousness is certainly mysterious, but I don't think solving the measurement problem requires invoking consciousness. Decoherence explains why the world appears classical without any reference to conscious observers. Measuring devices, whether conscious or not, interact with quantum systems and become entangled with them, spreading superpositions into unmeasurable correlations with the environment. But there is something deep about the relationship between information and reality that we don't fully understand yet. Quantum mechanics is fundamentally about information. The wave function is information. Entanglement is correlation of information. Measurement is acquisition of information. And information is not nothing. Information is physical. It takes energy to process, space to store, time to transmit. Information might be the most fundamental thing there is. I sometimes wonder if the universe is information, not information about something, just information, patterns, correlations, structure. And what we call matter and energy and space-time are just ways of organizing that information, ways of describing the patterns. This is philosophy now, not physics. Physics can take us to the edge of these questions, but it can't answer them, not yet anyway. Maybe someday we'll have a theory that explains why there is information rather than nothing, why the quantum rules are what they are, why this particular universe rather than some other. But we're not there yet. What we do have is quantum mechanics, a framework for understanding reality that has been tested and confirmed beyond any reasonable doubt, a framework that reveals a universe stranger and more wonderful than anything we could have imagined, a framework that, after a century of argument and confusion, still has the power to astonish. The silence between measurements, that's where the mystery lives. In the gaps between observations, when the wave function evolves smoothly, according to the Schrödinger equation, when superpositions build up and interfere, when entanglement spreads through the universe, that's where quantum mechanics does its work. That's where reality, whatever it is, takes shape. We observe only glimpses, snapshots. the measurement outcomes that punctuate the quantum evolution. Between those glimpses, we have only the mathematics, the wave function, the amplitudes, the phases, and from that mathematics, we reconstruct as best we can the reality that underlies our observations. Is the wave function real? Are the many worlds real? Are the quantum correlations telling us something about the nature of existence that we don't yet understand? I don't know. After 50 years, I don't know. But I'm still asking, still calculating, still marveling at what we've discovered and what remains to be discovered. Quantum mechanics is not weird. It's the universe. We're the weird ones for expecting anything different. We evolved to navigate a classical world, to track objects with definite positions, to predict events with definite causes. Quantum mechanics tells us that this classical world is an approximation, a coarse-grained description, a shadow on the wall of Plato's cave. The true reality is quantum, superposed, entangled, indeterminate until measured. And once you accept that, once you really internalize it, the apparent weirdness dissolves. Of course, particles go through both slits. Of course, measurements create the properties they measure. Of course, entangled particles are correlated across vast distances. That's what quantum reality is. That's what we are. Patterns of quantum information in an unfathomably rich quantum universe. Go outside tonight. Look at the stars. The light hitting your eyes is made of photons that have been in superposition for millions of years. Their wave functions spreading through the cosmos until the moment they collapse onto your retina. You are collapsing wave functions right now. Billions of them every second participating in the great quantum dance that is reality. And in the silence between those collapses, in the moments when you are not observing, the universe continues its quantum evolution, building superpositions, spreading entanglement, computing the future from the past according to rules we're only beginning to understand. That's what quantum mechanics is really about. Not weirdness, wonder.